All right, in the visible spectrum, who has, Max just said that the red had the longest wavelength, so who has the shortest wavelength? Well, violet, actually. So Roy G. Biv, the last one on there would be violet, wouldn't it? All right, let me ask Ty, which, on the visible spectrum, which one has the highest frequency? Violet, that's true. Okay. Let's see, Davis, which one has the highest energy? Right, very, very good. Did everybody get that? Okay, so we know that light has a dual nature. It travels kind of like a particle. What do they call that little bundle particle of energy? I'm going to call on, let's see, Elizabeth. What do you call that little bundle packet of energy that acts like a particle? What is it? Oh, I like that term. Now, electromagnetic energy is all that. That's light. Electromagnetic energy is light. But what do you call the little bundles of energy that they think act like particles when light travels? I made a joke about traveling light. He said, "Oh, now I get it." No. What about? Anybody know? What is it? A photon. Okay, remember that? Photon. So the theory is that violet photons would have more energy per photon than a red one. Okay, so if you understand that, then we go to the I think the good part. This is the good part here. Now, what I'm going to do today is a demonstration kind of like this one. I think it surprised them when they were doing experiments and they wanted to excite electrons. And when you want to excite electrons, you can do it with heat or electricity, or you could use microwaves, you could do something else. And there were a lot of people that thought that you could take an electron and just make it a little bit more higher energy, a little bit more excited, a little bit more, and they thought it was like a ramp, like that. But it wasn't, and that's what surprised them, and that's where the quantum model came from. It says the electrons are not like that. They can't excite them a little bit more. You have to give them an entire, what do you call that, amount of energy it takes to jump from one place to be excited. I need to give the whole amount of that energy. What was that called? Kayla, do you remember that? It's a Q word. Yes. If you give me a whole quantum of energy, I'll make the jump and I'll get excited. And so the electrons can't just be found anywhere. Let's say they're about here and you excite them. If you don't excite them with a full quantum of energy, they're not doing anything. You give them a full quantum, they'll go to the next level higher, they'll get excited. And they won't do anything until you get another whole quantum. At least quantum is not the same either. It's not the same from one jump to another. And so here we have this diagram here. Excuse me. Now remember, electrons where they're normally found are called the ground state. The ground state is where they normally are found. That's their normal energy amount. But when they absorb energy, they jump to a higher or excited state. Now you can't tell that. You cannot tell when they're absorbing energy. But then they're going to fall back to their ground state. So watch. Ready? Absorb energy, release energy. Absorb energy, release energy. Absorb energy, release energy. So when they release the energy, many times it's in the form of visible light. And you can actually see a color. And so here, see this right here? All right, which one of these, 1, 2, 3, or 4, which one of those is the greatest difference in energy, the greatest amount of energy given off? Let me call on Tyler. Which one of these, 1, 2, 3, or 4, which one represents the greatest amount of energy being given off? 3. Now go up here. which one of these colors do you think were produced by that high energy being released? Which one? Yes. Everybody see that? Violet? Okay. All right, is that right? Okay, ready? Okay, Jonathan, which one of these do you think shows the least amount of energy being released? Okay, and so which color do you think would be associated with that one? Which one? Yeah, kind of an orangish red. All right, and then what about the second highest amount of energy? How about the second, Caroline? What about the second highest amount of energy? Okay, that would be this blue one here. And then the last one, the next to the smallest one, 4 would be the other color, green, like there. See that? So what you're going to see is they did not know when they saw this. Did you see a list on the video? Didn't they have something like this in the video? Were they looking at this stuff? Didn't the person look at it and see a spectrum of colors? And so they, as a matter of fact, for a long time, when somebody said, "Hey, I discovered a new element. I discovered a new element." Oh yeah? How are you going to prove that? Well, one way they could prove it is they could heat it up, excite it, and look at it. Look at its spectrum here. This is called an emission spectrum or a bright line spectrum. Same thing. So a bright line spectrum or emission spectrum, and they say, "Oh, sorry, that emission spectrum is the same as another element. I'm sorry, that's not really a new element, and you don't get credit for discovering a new element." And so for a long time, that's how they knew if you discovered a new element, because every element gave a different fingerprint. Now, I say the word fingerprint. It has nothing to do with fingers, but this is an identifier, isn't it? And every element had its own particular set of colors. Does that make sense to you or not? See, I don't know. I know when I was your age, I didn't know. I never saw this demonstration. Nobody ever used the word quantum with me. I didn't know it at all. But the more I learned in science, as I was taking more and more, I even found out this. You could look at the light from a star. You could look at the light from a star and do the same thing here and find out, you know what? I think there's hydrogen on that star. Nobody went there and nobody sampled it and said, "Here, I'll bring it back to Earth and we'll analyze it." No, they used the light, and they analyzed the light that came from it. And that's how they can tell how different stars have maybe hydrogen or helium or something like that. They use this a lot. There's another one. I want to mention this briefly. It's not in the book at all. Do you know if you were to take one of these, and I'm separating the colors. If I look at one of these from the sun, I would get every single color. It would be an entire rainbow. I would get every wavelength you can think of, but there would be some that were missing. It's almost like I'm looking at the entire rainbow, and then somebody took and took away some wavelengths. And so, what's that about? I'm expecting the whole rainbow, and there's some that are missing. Has anybody done eddy reading? Have you ever thought about that? Why there would be some missing wavelengths in the rainbow? And if you have time, I have a poster back there behind that door. Behind that door, if you go back there, they have one of the sun. And you'll see where there's some missing wavelengths of light. And this guy named Fraunhofer, what he said is, I know what's going on. The energy given off by that sun is enough to produce every wavelength. You should see the entire rainbow. But that light, before it gets to the earth, it has to pass through the sun's atmosphere. It has to pass through the sun's atmosphere, and the sun's atmosphere actually absorbs certain wavelengths, and by the time they get to the earth, they're not there. And these missing things, that's called an absorption spectrum. Well, that's pretty neat. I've seen people do this, where they say they have something like CO2, and then they shine light through it, and they have the rainbow. Roy G. Biv, and they expect to see the whole rainbow here. Get that? and you see, blah, 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 you see all the colors, and then you'll see some that are missing. And that's called an absorption spectrum, which means that I should see all of Roy G. Biv, but CO2 must have absorbed certain colors. And now we know that, here's something else they do. I'm getting a little bit in astronomy here, but it's pretty neat. I don't know how much you know about astronomy, but do you know that stars kind of keep their positions relative to each other, even though they go across the sky at night? They're not really going across the sky, it's us rotating. Okay, so they kind of stay where they're at, but planets are, you'll find them here next to these stars, and then they move, okay, during the day-to-day day. Well, every once in a while, a planet, here's a really bright star, and a planet will pass, it'll be passing this way. It'll go this way. And so what they do is they focus their diffraction grating onto the star, and they say, I got you, I got the rainbow, I got everything, all right? And then when the very edge of that planet gets in front of the star, they notice that some of the wavelengths disappear. Now, what if the wavelengths that disappear match the ones that happen in the lab of CO2? Then what do they know? That planet must have CO2 on it, even though they've never been there. So there's a whole lot of stuff in science that have been discovered by using light. So let me go ahead and do the demonstration for you, and then I'll come back to the rest of the chapter. Now I need to turn off all the lights. And also, if you're sitting, you might have to move. All you have to do is move back to that table right there. And I got to get as dark as I can here. If you just, all you have to do is move. I'm going to sit here. I guess you just move back there. All right, so what we have is, let me plug this in. Oh wait, I'll tell you before I plug it in. We'll do something else. Now, all right, what this is, let's call it a spectroscope. Spectro means you see a spectrum, scope means to see, spectroscope. Okay. Now the way you use it is not intuitive, so I have to tell you how it is. You see this big fat end? That does not go by your eye. The little end goes by your eye. That's the first thing. I usually like to have this straight part. I like to use my right eye. That's a few. But what you have to do is, excuse me. Here, I'm sorry, my fault. See this little slit right here? This is how the light comes in. So the light's going to come in through the slit. So I'm going to line that up. I have my slit right here, right? I got my slit. Now, I'm going to line this up and let the light come in. But I'm not going to look at the light. I'm going to look over here. So it's not that hard. You put this next to your eye. Right now, I already see the light from that window, but I don't want to look over here. And then what I'll see is a spectrum of light, and there's a little tiny ruler in there. And when you see that 4, 5, 6, 7, that's 400 nanometers, 500 nanometers, 600 nanometers. So I'm going to give everybody one of these. All right, so you can be the hostess. Let's take one. This one here. All right, everybody go ahead, and we're going to get one of these spectroscopes. All right, get one for you guys. Now, right now, it's sunny out, and the sun is hitting buildings, it's hitting cars, and even though the blinds are drawn, you can actually look over there and probably see a spectrum. I'm going to try to make a brighter light for you over here, but let's try it again. You hold the little end by your eye, and you line the slit up with the light source. Everybody see where the slit is? But you don't look at the slit, you look over to the other side, and then you'll see a ruler, and you should see a spectrum. So if you look at that window there, you probably should be able to pick up a spectrum there. And I'll make a brighter one over here in just a second. Now let me know if you don't see a rainbow. Let me tell you, if you don't see a rainbow, let me know. Remember, line the slit up with the light source, but don't look at the slit, look over to the left of it. Now if you have it upside down, you might look at the right of it. Does everybody see a little ruler in there? All right, let's go over here. I'm gonna turn this light on, it's a little bit brighter. Wait, you put it like this one? All right, ready? This should be pretty bright. All right, so this thing, this, uh-oh. Wait a minute. I'm gonna get electrocuted. I think they use these for play, and I don't think that's the way we gave it to them. I know it is.
Oh, John, we only got 5 more.
Okay, try again.
Oh, shoot.
Now, you should see a pretty bright rainbow, is that right? Is everybody getting it? Now, what I was talking about a while ago is, if I don't have a big bottle of CO2, but if I were to put a big bottle of CO2 in front of this, then you would see some of those wavelengths being missing. That's called an absorption spectrum. What you're seeing now is probably the full spectrum. Is everybody ready on that? Everybody get that? All right, I'm gonna turn this off and let your eye kind of get used to being a little darker now. All right, now. Here's that one. Now this right here, this tube, it has hydrogen gas in it. What's that look like? Nothing. Okay, it looks like nothing. And so what I'm going to do is, hydrogen does not really look like anything. What I'm going to do is I'm going to excite it. Okay? I'm going to excite the atoms. I'm going to excite the electrons of hydrogen. And I want you to look at it without the spectroscope first. Without the spectroscope and say, oh, I see that light. But really, that's not what's hitting your eye. There are many, many wavelengths in your eye. Let's see what wavelengths are made there. Now, if you're sitting really far away, you might not be able to pick it up, but if you want to move up closer, this is probably the dimmest one that I have. But if you want, you can even sit here if you want. Are you guys seeing color? Are you guys seeing bright lines?
Yeah, they're just lines.
Now, if you want to do a serious study on this, you could get a pencil and paper out, and you could try to draw what colors you see and about what wavelengths they are. All right, is everybody okay on this? Now, I want to show you that the fingerprint of hydrogen is those bright lines right there. I'm going to let that cool off just for a second, and I'm going to get another one out. This one is a gas called argon. And that's this is in English, this is the past tense of have went, argon. Anyway, argon is argon. It looks like nothing. See that? It looks like nothing. But if I excite it, these electrons are arranged differently. They'll make different quantum jumps. They're going to make different quantum jumps, and it should be, oh, that one you really got to be close. This is the worst one, sorry. You won't be able to see it very at all. If you want to come up here, you can. You want to sit down here? Yeah, just don't eclipse everybody. You're down kind of low. And the best one, I'd say the best one for last, but this one's not very, but if you were to do a serious, if you want to do an extra project, you have to sit here and try to carefully write down where these lines are and what color that's going to be. All right, how about the best one? You want to do the best one?
Yeah.
That one, unfortunately, you have to be kind of close. Just stay where you're at, please, stay where you're at. Now, this one. Let's take a look at this. This is hold on.
Oh, shoot. Yeah, we got like 2 more minutes.
All right, go. All right, see this? This is neon. What's neon look like? Nothing. You have the air. So what we're gonna do is this should be cooled off by now. This is the best one. Again, neon's electrons are in a different arrangement, and so when they take quantum jumps back and forth, they'll give you a different fingerprint. This one you don't have to be as close to because it's really bright. Look at it without the stroboscope, and you never knew that all those other colors were actually hitting your eye at the same time.
Whoa.
Give me some colors. Wait, you see green? Green? I can't believe there's green light hitting my eye. Orange, I can understand orange and red. Green, how about purple? You see any violet? Now, I'm hoping that my little mini lesson about quantum jumps, I'm hoping at least you can think more about it and say, why would this give us a different emission spectrum than the other one? Because their electrons are in different arrangements to begin with.
No.
Okay, let's go ahead, and if you don't mind, put those, we're going to put those back in here. I don't have these here tomorrow. You said, I really need to spend a little extra time on that. I'll be here at lunch today. Easy.
Whoa. Bro.
Oh, jeez.
He said like we got to get back on track. Like, a couple.
Okay, so let me get this started again.
Oh yeah.
I'm hoping that made this part of the book make a little more sense to you. I have back here, back where the when you first come in the door, I have a poster. I haven't put it up on the room yet, but it's actually an emission spectrum for many elements. And if you just take a little time and look at it, you'll see every one of them is slightly different. And it actually is an identifier. You can use it to identify elements. All right, let's go to this next person. And we said part of this chapter has to do with scientists. And you probably heard this person's name because I think Miss Founds, I don't know about the COVID year, but did you guys do Bohr models?
Yes.
You do like the first 20 elements or something like that, or the first 18 elements? Do you remember drawing a drawing where you put like so many protons and so many neutrons, and then you had the first, and some teachers like to call them rings. I never call them rings, but the first energy level, did you put like 2 dots? And you remembered, oh yeah, the first energy level can only hold 2 electrons. And then the second one, did you put like 8 dots? Okay, and you say, well, the second one can only hold a maximum of 8. And then you had 8 in the third or something like that. You guys did something like that, right? Well, this model, the Bohr model, is great for teaching certain things. But let's talk about this guy. What did Bohr do? He made the model. He believed, and I get it. He believed that the electrons were orbiting the nucleus, and they were going like planets. That wasn't a bad idea, you know? Imagine that. Here's the sun, and the planets go around the sun, and so maybe the electrons go around the nucleus, like, and even in elementary school, and even in 9th grade, you probably thought that's what they do. That's okay. That model was used to tell you that the first energy level they're called the lowest energy level, and it is the smallest energy level, and it can only hold a maximum of 2 electrons. So I like the Bohr model because it taught all of you that the first energy level can only hold 2 electrons. Everybody got that? So if you were hydrogen, you would put your one and only electron right there. What if you're helium? I put my first 2 right there. And then I want you to look up here. This is where it gets kind of good. Look at the periodic table. How many elements are in the first period? And by the way, I may have to get a new laser here. I think my laser ran out. But we got a little bit left. Periods are these things here. Period 1, period 2, period 3. Periods are horizontal. Get that? These are called groups or families. See that? 18 of those. So the first thing you notice is that the first period of the periodic table only has 2 elements in it. Only 2. Why? They're the only elements in the universe that only need 1 energy level. That's why they're in period 1. Who's the first element that cannot put all their electrons in the first energy level? It's got to be him. What does lithium do with the first 2 electrons? The same thing helium did. What are you going to do with your third electron? Put it in the first energy level. You can only put 2 there. You got to put yours in the next energy level. Oh, okay. So that's why lithium is the first element in the second period. Now, look at this. How many did you say the second energy level could hold? How many? From last year? 2 in the first, and there's how many? How much? 8. Watch. 1, 2, 3, 4, 5, 6, 7, 8. Oh ho ho. Now I understand why there are 8 elements in the second period. If you're in the second period, you have at least 1 electron in the second energy level. Now, who fills the second level? Which electron fills the second electron? Which electron fills the second energy level? Electron number 10. 2 in the first energy level, 8 in the second, that's 10. And all of a sudden you might be seeing something. Wait a minute. When you filled the first energy level, you were a noble gas. I don't want to gain. I don't want to lose. Leave my electrons alone. I'm very stable. When you put 2 in the first and 8 in the second, what does that mean? I'm a noble gas. Don't leave me alone. I don't want to gain electrons. I don't want to lose. I don't want to form compounds. Leave me alone. Is this starting to make sense a little bit? Whoa. Okay, so we're going to get into this a little bit, all right? We're going to get into this whole thing called electron configuration. All right, let's read a little bit. So even though Bohr thought that the electrons were going in circles like orbits, that was very, very, very soon, that theory was thrown out the window. It actually worked for a while. If you had a hydrogen and you excited the hydrogen a little bit, that 1 electron would make a jump and would give a color. Excite a little bit more, it'd make another jump and another jump. And that would have been nice if they were like in little orbits, but as soon as they got past hydrogen and they started doing experiments with other elements, that model did not show to work out. So I'm okay with the Bohr model as far as teaching you a little bit of things, but right now we have 0 evidence that electrons are going in circles around the nucleus. You got that? So what are they doing? Okay, you're not going to like this. There's a lot of things you're not going to like here, okay? Let's read. Can everybody want to volunteer to read here? Read the first, maybe paragraph, 2 paragraphs. Don't want to volunteer? Okay, go ahead. In the mid-1920s.
By the mid-1920s, it had become apparent that the Bohr model was incorrect. Scientists needed to
Pursue.
pursue a totally new approach. 2 young physicists, Louis,
De Broglie.
him, from France, and Erwin
Schrödinger.
from Austria, suggested that because light seemed to have both wave and particle characteristics, it behaves simultaneously as a wave and as a stream of particles, that the electron might also exhibit both of these characteristics. Although everyone had assumed that the electron was a tiny particle, these scientists said it might be useful to find out whether it could be described as a wave.
Wow, can an electron be described as a wave? That's, all right, one more.
When Schrödinger carried out a mathematical analysis based on the idea, he found that it led to a new model for the hydrogen atom that seemed to apply equally well to other atoms, something Bohr's model failed to do. We will now explore a general picture of the model, which is called the wave mechanical model of the atom.
Okay, so if you're keeping track of scientists, let's go back. I'm going to go back to my page where I started writing scientists down. All right, what do you, this next scientist I should have put down here was Bohr, right? And Niels Bohr. And he had a kind of a planetary model, wasn't it? Of electrons orbiting the nucleus, right? What did who are the scientists that Caroline just read about? We're going to put them together. What what was the name? What was that? Probably never seen that name before. De Broglie. And what's the other word? What's the Austrian's name? It's kind of a German sounding name. Schrodinger. I'm going to spell his name right. SCHRODINGER. All right. They came up with the wave mechanical model. What they were saying is that maybe the electron shouldn't be thought of as a particle, but more as like a wave. And that was very mathematical, what they did, a very mathematical model of the electron. And that's de Broglie and Schrodinger. All right, let's go on down. Now, what I'd like to do is we'll talk about, and the book left out this person's name, and his name is Heisenberg. Now, I don't know if you ever watched the series called Breaking Bad. Did you ever see that? It's actually based on chemistry. It's got chemistry stuff in it, but it actually is about drugs. Well, anyway. But later, they didn't want the drug people knowing his real name. He was like a science teacher, high school science teacher, you know. And so, what's your name, you know? And he just came out of his mind and said, Heisenberg. And so from that point on, his name, all the drug people, that was Heisenberg. And they weren't smart enough to know that Heisenberg was a famous scientist in chemistry. But anyway, Heisenberg came up with probably the theory you're not going to like. It's called he got famous by being uncertain. He said, Heisenberg's uncertainty principle said, if we were to try to find out where an electron is, if we want to find the exact position where it's at, then we lose the ability to find out where it was coming from or where it was going to. So if you were in a dark room, did I talk about the dark room analogy before this? You're in a dark room and you go to one corner of the room and maybe one little bee lands on you and stings you and you said, oh man. And then you said, I'm going away from that. And you went to another corner of the room and you got stung 5 or 6 times. And then you went to another corner, you didn't get stung at all. It's really dark, you have no idea, you never saw where the bees were coming from. As soon as that bee stung you, you lost the ability to know where did that bee come from. He could have been here and came right around my arm. We don't know where it came from. And once he stings me, I actually don't know what happened to him after, do I? And so Heisenberg said, you'll never be certain about the location of the electron at the same time you would know about its momentum, where it was going. He wasn't a great driver either, because one day he was driving and he got pulled over and the police said, do you know how fast you were going? He says, no, but I know where I was at. So anyway, if he knew his position, the more he knew about his position, the less he would know about his motion. You don't like these jokes, do you? Okay. So these are like the higher nerdy jokes. There's the easy nerdy jokes and the little bit higher ones. That's it. So anyway, here's what they came up with, and I want you to think about this. See this picture? It's kind of like fuzzy, and it's a little bit darker orange here, and then it's not as dark here. That shape, some of your elementary teachers or middle school teachers might have called that an electron cloud. Did you have a teacher ever use the word electron cloud? First of all, electrons are not sitting still. They're moving at close to the speed of light. So they're moving all the time. Don't ask me what they're doing because I don't know. But they did a thing, this is very mathematical now. The electron now has become a mathematical model. And this is called a probability map. What are you doing, electron? I don't know. I will never know. But I do know that about 90% of the time, you're in somewhere in that shape. I don't know what you're doing in that shape, but probability-wise, you're in this kind of a thing. Are you with me at all? And I know what you're saying. Well, what if, is he going around a circle? We don't know. Is he going across? I don't know. Is he making figure eights? I don't know. And I know you don't like that. I don't like that, but this is what you're going to see. This is the modern atomic theory, the model, okay? So I'm going to go over here, and they have a name for that. That little location, that zone that you will find the electron in 90% of the time is called an orbital, okay? It's an orbital, and it's a probability map. Now, we have orbitals that have shapes like this. Some of the orbitals have a shape that's kind of like a ball, okay? And those are going to be called S orbitals. Now, an S orbital is kind of like a ball, and we have S orbitals in the first energy level. If you're in the second energy level, the S orbital is bigger because the second level is bigger. If you go to the third energy level, there's an S-shaped orbital. It's even bigger. Every energy level has an S-shaped orbital in it. Now, I don't know if this book, yeah, here it is. So this book shows what they call is a 1S. 1S means in the first energy level, and you find yourself in one of these little orbitals, we're going to call you a 1S. Your home is 1S home. And if you're in the second energy level in this kind of a round probability zone, that's 2S, 3S, 4S, 5S. Okay, are you with me? Check my time here. 10:30? Okay, I got it. All right. Now, in the first energy level, okay, in the first energy level, level number 1, what you'll find an S orbital. Now the S orbital looks kind of like a ball, and you can put up to 2 electrons in an orbital. So you can put 2 electrons in an orbital. And so what we're going to do is start this thing called electron configuration. All right, I'm just going to scratch the surface today, and then we'll do a whole lot of it tomorrow. All right, if you are hydrogen, if you're a hydrogen atom, how many electrons do you have? 1. Let me tell you where that electron is. It's parked in the first energy level, the lowest energy level you can come into. It's in a S orbital, and there's 1 electron there. So if somebody said, what's the electron configuration for hydrogen's electron, you'd say 1s1. In the first energy level, in an S orbital, you'll find 1 electron there. Let's do helium. What do you think about helium? How many electrons does helium have? Everybody in the room should know that. 2. Where are they? Do you think you might have 1 in the first energy level? Are they going to be in, and can you put another one in the S orbital? Every orbital can hold 2 electrons. I'm going to put both of them there. Oh, I see. So if an atom that only has 1 electron, you're going to park the electron in a 1s1 slot. What if you have 2 electrons? 1s2. In the first energy level, in the S orbital, I'm putting 2 electrons there. Here's where it gets interesting. Let's do lithium. Guess what lithium does with 2 of its 3 electrons? What would lithium do with his first 2 electrons? Wouldn't he park them in the same place helium did? Wouldn't he? But doesn't he have another one? What's he going to do with the third one? Can you put 3 in an orbital? No. You can't put, as a matter of fact, you can't put any more in the first energy level. You got to go to the second energy level. And what's there waiting for you? An S orbital. It's an S. See, two, not one S, two S. I'm ready. Oh, okay. Can I put an electron there? Sure. So how many electrons do you see here? How many electrons? 3. That's lithium, isn't it? All right, let's do one more. Oh, I'm sorry. Okay, let's do beryllium. How many does beryllium have? How many electrons? 4? What are you going to do with the first 2? I'm going to do the same thing helium did. Okay. Hey, have you got any more electrons? Yeah, I got 2 more. Well, you can't put them in the first energy level. It's full. You can put them in the second energy level, but where in the second energy level? In an s orbital. Can I put another one in there? Can I put 2 in there? Every orbital can hold what? 2 electrons. Yes, you can. Yes, you can. Got it? 1s2, 2s2. I'll give you one more, and this will mess you up. That's okay. If you get messed up when you walk out the door, don't even think about it. Did you know the second energy level is further away and it has more space? And so they found out that there were, in the second energy level, you had an s orbital, and then you had another kind of probability zone, which looked weird, really weird, kind of like a dumbbell. And they call that a p orbital, sp. And they found out there's this kind of p orbital, and another kind of p orbital, and oh man. Well, okay. All right, anyway, I'm going to stop there. And so thank you very much. Please, I did ask you to read this chapter. Don't put that off. I think if you start reading it now, a lot of things will come together for you. We'll do the configuration for at least 2 days in a row. You'll see me doing it on Friday, all day Monday. Got that?
Thank you.
Okay, you're welcome.